Hello, everyone, and welcome to week 2 of Artificial Intelligence. We're going to be talking about search this week, and there's a couple chapters in the book we'll go through that address search in greater detail. Starting off, though, we're going to talk about the assignments that are due this week. Then we'll move into the chapters in the text. So, drilling into the assignments, uh, this is the basic outline of every week that we'll be going over. So the idea here is to remind you of where we are in the progress, and this is week 2. So the main thing you're concerned with now is the discussion. However, you probably want to look ahead to week 3 and start thinking about your project for search. And in fact, you probably want to go ahead and submit your proposal so that we can evaluate it and have some time so that you can adjust if need be. So for search, speaking of, the idea here is that you pick a topic that is interesting to you, and do try to have some fun with this as much as you can. Obviously, this is a class where you've got to have a certain amount of AI related stuff, but it could be something that's fun for you. Feel free to use libraries, tools, and other code as a starting point, but make sure that you first of all give them credit and make sure that it's different enough so that you're not just turning in somebody else's work. The ways that I would probably approach this project is either to use Anaconda and Jupyter notebooks as the mechanism, or perhaps Azure Databricks Community Edition, depending upon the familiarity that you might have with that environment. Uh, Databricks Community Edition is a hosted version of a notebook-oriented Python type environment. Generally, it's focused on Spark. However, you can write just plain old Python there and so on. Jupyter and Anaconda is also a very good alternative. You may want to consider that as well. So, as I've mentioned before, 10% of your points come from proposing the search topic and receiving approval. So, you want to do that most likely through either messages or email so that we can basically capture it. You also want to make sure you memorialize that approval and proposal in the document that you submit so that it is a section where you talk about here is what was proposed and so on. Then you'll work on the implementation, 40% of it to get it working and addressing the thing that you're looking at. Uh, then also the remaining 50% is around the Microsoft Word document, which is going to be the documentation of the overall process that you went through. And basically, it's going to be things like the topic and domain, the algorithmic details, the challenges you encountered during the process, and so on. If you have any questions about this, do reach out to me. That's what I'm here for. But at a high level, start thinking about it. Right? It may be a couple weeks out in your mind, but it may take you some time as well. I would recommend you look at it sooner than later. This week's discussion is basically choose something out of the reading that was interesting to you and talk about it. Feel free to pick something that might align with what you're planning to do as far as your project, if you can do so. But the idea here is that you pick something that resonated with you, that you learned, maybe that was something you didn't expect, counterintuitive, whatever it might be. Pick something that's interesting and talk about it, right? And then make sure you do also respond to 2 of your classmates or 3, whatever the requirement is, so that you receive full credit for the experience. Moving into solving problems using search. So we have this concept of problem solving agents, right? So what is that, right? So drilling in, they're basically looking for answers. Um, and they're going to look for a sequence of actions that let them reach the goal. So it's basically figuring out what things need to happen to get to the goal state. So they may not have information from the environment, and they might even be able to get there without that information. But without that information about the environment, it's not going to be any better than basically just random trial. There's generally speaking this 4-phase process that things go through when you're solving these problems. You identify the goal, so it's formally called goal formulation. Then you figure out a plan to reach that goal, problem formulation. You'll start looking for ways to reach that goal, that's search, and then you'll actually do it, right? So that's a kind of an overall sort of approach to addressing this sort of problem. Interestingly enough, that sort of approach can work other ways in your life as well. So if you think about if you're wanting to achieve something, maybe in your career, you identify the goal, you figure out a plan to get to the goal, you start figuring, what is the plan that might get you there, and then you start looking for ways to do it. So actual working on a more detailed plan. Maybe there's multiple paths to get there, and then you actually do it, right? So that's one of the things about this course, because it is multidisciplinary. The things may have application elsewhere in your life. I know as I look back over my career, I'm amazed by how much I am impacted by the things that I learned during my master study concentrating on artificial intelligence. It influenced how I approach problems in general in software engineering, not just in what is considered an artificial intelligence problem space. So back to the content at hand, two kind of concepts here: open versus closed loop. Open ignores precepts, and it breaks the agent environment loop. It assumes knowledge of the environment is correct. So once you start going, you know that it's right. You assume that it is correct, and it assumes that the environment does not change and that the model is correct. A closed loop monitors the precepts during execution. So it assumes that maybe they didn't get it right whenever you figured out what the environment looked like. It's definitely safer than an open loop, because if something were to either have been perceived incorrectly or changed after the initial uh, sort of evaluation, or perhaps the actions that one is taking or the agent is taking isn't actually doing what you think they're doing, or maybe the rules of the environment are slightly different than what you think, then you won't know that unless you're actually monitoring that environment. Using a closed loop approach enables adaptation, and that's a key thing in correcting for things that are either assumed incorrectly, or something might have changed, right? So in general, closed loop, obviously higher complexity, potentially more resources involved and so on, but generally speaking, a better approach. Drilling into the search problems and solutions, um, you have a set of states. Um, and so you start with an initial state. It's your starting point. You have a goal state. That's where you're trying to get to. There's actions that hopefully will get you from one of those states to another. So they things to get from the initial state to the goal. So things you're going to do. Transition models is the result of each action that you take. Action cost function is typically some sort of numeric cost that is applied whenever you are using it, doing an action. Path is a sequence of actions where you might find your way to navigate through this state space. And then an optimal solution is going to be that path that has the lowest actual cost function. So it is the most, least expensive in terms of whatever cost function you're utilizing. And the state space graph is the states or nodes, and the edges are actions. So it's how you traverse through these various states. Abstraction. Basically, the idea here is that you're going to have a model. Models are going to be an abstract mathematical or code sort of construct of the thing. Extraction is about removing details from the model, or the thing that you're dealing with. And you can think of it as basically like zooming out, right? So if you're on like Google Maps and you zoom out, you're seeing less detail but more stuff. It's kind of that sort of concept. The level of abstraction is the amount of detail that you're seeing, so the amount of zoom level in that analogy. A valid is a representation of the real thing. So invalid would be that you're representing it, but it isn't really what reality is. Useful, so it lets you do something with less effort than actually dealing with the real thing, right? So if you have a model that is sufficiently detailed that it's really accurate, but it's easier to really deal with the actual thing itself, not so useful, right? So the idea and the goal of using models and abstraction is to have something that's simpler to interact with than the thing which it is modeling, or the thing that it is being used to abstract out. So drilling through kind of the concept of search, this is a somewhat of a real world sort of scenario. You might have seen these slider problems in the past. The idea is that you're trying to arrange a square of set of tiles with one of the tiles missing in a certain pattern. Um, you can only move a tile into a location where the opening is, so you can't move it to where there's already another tile in that square. And there's variations based upon the number of tiles, essentially of the size of the grid. What you see in the diagram is a 3 by 3. The box is a 4x4, so there's a total of 16 squares, one of which is empty. In order to play the game, you pop out where it says they're removed to play, and it lets you slide it around. The goal is typically to get it back into the order that it was originally. There may be other variations on it. It's a common sort of thing to be using inside of the AI world, because it allows you to represent things um, in a kind of it's a relatively simple search space, but there is a problem there that goes with it. So an example of it is this sort of thing, which is basically a slide puzzle. And I'll deviate here a little bit from the material and see if I can pop open the actual animated GIF um, and let it play. So here's the idea, and hopefully this is coming across okay. So this is shuffling it out, but basically the the actual thing you're seeing here isn't really solving the problem per se. It's basically unscrambling it when it previously was scrambled. But the basic idea is that you move around that empty square in a fashion that moves the tiles where you want them to go, and the goal is to get them into that order. It is a problem that can be addressed with a search algorithm, so maybe something to think about. Relatively simple, but the complexity of it depends upon the amount of tiles, right? The more you have, the harder it gets. Drilling into algorithms. So various types of search algorithms. Basically, the idea, as we've mentioned before, it's about trying to return a solution to a search problem. We have this concept of the search graph, where you have parents and children and you have edges. A search tree is a way of organizing that state, where any given state only has one parent is the basic idea. So it is a tree. Um, and the way that you're solving this problem is typically by working your way down from an initial state down to the goal states or somewhere in the bottom. And each time you're traversing one of these edges, you're potentially incurring some form of a cost. So the sooner you solve the problem, the better. But you don't necessarily know where the solution is until you expand out that sort of thing. The So each of these nodes is essentially a state that is associated with actions that occurred in the previous state to get you to that state. The parent is obviously the node that points to the child. So it's the one that you started with, and then you make changes to it and you move down through the thing. As you can see, even with relatively simple stuff, this gets pretty big pretty quickly. The edges in the tree is where you do the actions that change the state, and you expand a node whenever you go down to a given node and you consider the possible states that can result from various actions at that level. And when you do that, you generate a new node underneath of the state that is basically all of the legal moves that you're allowed to do based upon the rules of the environment that you're working in. The frontier is the unexpanded edges that are unexpanded nodes that you're working through. So uh, that that's referred to as the frontier, because you don't necessarily know the answer to it just yet. So there's various types of searches. The best first search is at each frontier you choose the path with the best local value, and that's a key thing. You're looking at sort of local values relative to its node. So you've got potentially two or three choices that you might have at the node. You choose the one that has the best cost function or value function at that point. So you're looking at it very narrowly. This is susceptible to what's called a local minimum or maximum, depending upon which way you're trying to solve the problem, which means that you might find what looks like a good solution, but you're not really evaluating the entire search space. It could be you have to make a less efficient choice early on to get to the true best choice overall. It's not a great strategy from that regards, because you may miss the real value. But regardless of the search approach you're using, you have some data structures that you need in order to do the search. Um, One of those, and I'm going to pause for one moment to see if I can stop. Sorry, I attempted to pause so that things would stop popping up. So whenever you're talking about the data structures that are required for search, you have this concept of a node. It has state associated with that node. There's a parent, there's actions that got you to that node, or potentially actions that are coming from that node. And then to take those actions, there's this past cost. So you may actually be keeping track of the cost that cost you to get down to this given node. So each individual node has essentially a cost associated with it, and that's what that G of node is. The frontier typically is going to be something like a queue of some sort. It could be a priority queue. It could be first in, first out, last in, first out, which is basically a stack. It could be various types, but you're going to keep track of those nodes that are at the edge of your evaluation. Typically in some sort of a queue, you're going to do push and pop on that queue. You're going to remove queues from it as you, or remove nodes from it as you take them from being the frontier to something that's you've already evaluated, which will oftentimes generate more nodes that become the frontier. You're going to take the top function to typically peek sometimes into what would be the top to make some determination. And then whenever you've expanded the frontier, you're going to be pushing those nodes that now are the frontier into that structure. Sometimes there's multiple ways to get to the goal state. The worst case, in a lot of ways, is a loop or a cycle. So you might have, if you're not keeping track of what you're doing, and if perhaps your data, maybe your states aren't truly um, a tree sort of structure, you might end up in a loop, and that's not ideal. So there's ways to avoid that. Some, and in the quote here is kind of humorous, algorithms that cannot remember the past are doomed to repeat it. So you may keep track of if you've been to this node before. So you may check for redundant paths using essentially a graph search. If the thing that you're doing has rules which prevent cycles, like if you're playing chess, you don't really get cycles. You're not going to go back into a loop or something because your pieces can only move a certain direction, especially if a move results in a piece being taken, or whenever you move, somebody else moves, that's going to change the state such that it's unlikely you're ever going to get back to that same state, right? Theoretically possible, highly unlikely, right? But if it's tree-like, you don't have to worry about it too much. The cost function evaluations oftentimes will take care of this, so that at the point that you reach a certain cost function, you may decide no longer to evaluate it until you've done some other exploration. So you may kind of pause those ones that are getting expensive because they're in a loop. But in general, though, you may need to keep track of what states you've been to so that you can not revisit them again. So when we're talking about how do you know what good is, so problem solving performance, there's several ways here to think about these. There's the completeness of, will you find a solution if one exists, and say if with certainty that one does not exist if one cannot be found. That that has an implication of being expensive computationally, because you're basically going to have to evaluate every possible node in the state map, right? State graph. You're going to have to go everywhere to see what is the real solution. Um, so you're going to ensure that you're going to basically find it if it's there. Uh, Cost optimality is can the lowest cost path be found, basically, so the lowest cost solution or path. Again, to know that with certainty, you've got to evaluate all of the possible states to find the one which is potentially expensive. Time complexity is literally the clock time or state transitions to solve the problem. So how long does it take you to find the solution? And that's going to be a product of the number of nodes that can be produced, the number of decisions that can be made. But you can think of it simplistically. If you've got two decisions at every node, you're looking at something that's exponential by nature, right? So these search graphs get very large quickly. uh, the space complexity is the amount of memory that's required to perform the search, which means if you're having to restore the number of states that you're going through, at very least you're looking at the number of edges time plus the number of nodes. So number of vertices slash nodes plus the number of edges. So if you're dealing with something like, say, Go, which is a game that has a great many number of states, it may become impractical to store all of them and evaluate all of them simply because of computational resources. So there's several ways you can do searching. The An uninformed search means that you don't necessarily do anything terribly smart. You either go breadth first or depth first, and you may do some sort of bidirectional search where you start both at the beginning and at the end and try to work your way towards the middle. But you're doing so kind of in a brute force sort of way. You're not really doing anything intelligent other than you're going to look at everything, right? And it's uninformed in the sense that you don't really know if one path is better than another or not. It is oftentimes the starting point for many of these sort of searches, because if the search space is relatively small, maybe okay, right? But as you get bigger, it becomes more of a problem. Uh, so uh, you basically, these are not necessarily bad ideas, but you make sure that you know what you're doing when you select them, because they may not do as well as you would like. So drilling into, well, okay, if there's uninformed, there must be informed. So what does informed mean? Well, it means really heuristic. Heuristic is nothing more than a rule of thumb. It's some sort of an approach that says, okay, this is likely going to be a good approach. And there's various sort of well-known ones of these, such as the A-star search, which is going to consider basically the cost of each node, plus a certain amount of a heuristic function to figure out what might likely be. And it's as simple as add those two things together to figure out which way you want to go. Um, there are downsides of heuristics because it may not be complete, right? You may miss, and it may not be optimal. You may miss the optimal solution. And using a heuristic, you may not find a solution that exists because maybe your heuristic doesn't make that wrong turn, what seems like a wrong turn early in the process to get to the real solution. And we'll talk more about that in the next chapter when we talk a little bit about the potentials of local maxima and local minima. So when we talk about heuristic functions, this is literally the function that's going to be governing the behavior of this informed or heuristic based search. Um, and you basically figure out some sort of way of um, of minimizing the amount of nodes that you have to go to. And you may use some sort of pattern database where you basically start looking at this segment of the tree looks a lot like this other segment of the tree. And so maybe you store the patterns. So whenever you start encountering one, you know what to do. And basically, to some extent, you could think of that as some form of abstraction. But one of the things you'll notice with this is with any kind of algorithm sort of analysis, you're oftentimes trading off storage for speed or effort. So, and that's where the things like this pre-computation comes in, to where you may literally calculate all of the optimal paths in advance, especially if you're going to be doing something like playing a game or something. So you calculate them in advance so that you can quickly determine the fastest rate simply by looking at, you're in this state, here's the fastest solution based upon that state, and give the cheapest solutions based upon that. And with that, we've talked about that chapter, and we can move into searching in complex environments. And this is where it becomes more interesting because you're actually dealing with the problems we talked about of local searches and hitting not necessarily the ideal solution. So the this is a pretty interesting sort of. I'll drill in on the slide a little bit so that you can see. You got a little robot. He's trying to find the goal up here, but he may get up to this little trough and think that he's there, right? Or that whenever he gets here, he may think he's there because he looks down and, oh no, it's this is down from where I'm at, so it's not better. Same thing can happen up here. This is called a shoulder. He gets up to this point and thinks, well, this is the same as where I'm at, so I'm just going to stay where I'm at because this is obviously the best place, and it was even better than this one, right? But the reality is, he needs to keep going until you find something that's even better. So, drilling into that a bit more, whenever you talk about local search, you're talking about a start state, and then you look around you. So the neighboring states that you can go to, and you don't necessarily keep track of how you got there, right? So it's very uninformed in that regard. You're just looking around. Hey, that's better than this, so I'm going to go this direction. And it sometimes works out okay, but only if the search space doesn't have some interesting characteristics or behaviors. Hill climbing is whenever you're trying to find the maximum, and it's like the name implies, you just keep going uphill, and eventually you'll think you've reached the top. The problem is you might reach the top of a hill, but not the top of the mountain, because it's, you got to go down to get to it. The other kind of the inverse of that is the gradient descent, where you're trying to find a global minimum. Rather than climbing the hill, you go down the hill until you get to what you think is the bottom. You may or may not be at the lowest point because you may need to go back up before you can go down. So the basic idea here is to keep track of this edge or the fringe, to ensure that you're um, potentially going to get completeness, although not necessarily that's with a tree search. But whenever you're doing a local search, it's about improving a single option until you can't make a better one. So you're not necessarily going to be looking everywhere, and you pick the one that is the best, but you may have actually missed the one that was the overall best, and that's the downside of it. The benefit of that approach, though, is it's generally faster and more memory efficient, because you're trading off completeness and optimality for quickness and speed. It may be fine, may not be ideal. So the basic basically another way of looking at that is you start in a random location, you move to the best neighboring state. If there's no better place, then you're done, right? So what's bad, right? Well, you start here, you move this direction, and oh well, that's the local. You move this way, you get up here, you go till there's something better. There's nothing better, so I stop here. And so you're again, as I mentioned, you're susceptible to local minima or maxima. Looking at that same thing in a different sort of way with some fancy names of what these things are. You've got a shoulder, which is a flat spot that you may think is it. You've got the global maximum, which is where you would actually want to be, but you only get there if you start in the right location with this sort of approach. You may, if you started over, in the middle here, hit this flat local maxima without really ever having found the right one, or you might even hit this local maximum because you started and moved that direction. And part of the problem here is these sort of approaches are random in nature. So your results may depend upon literally the roll of the dice of where you started. There's various types of these sort of hill climbing sort of algorithms. The simplest is the greedy one. You go basically similar to the steepest ascent. You find a flat spot. If you hit a flat spot, you keep going because you think you're on a shoulder. uh, you choose an uphill move randomly, so you basically there's some randomness thrown in, and so on. The random restart, once you think you've got it, you pick some other random location and go again. Maybe if you get a better value, maybe you weren't really at the maximum. The problem with any of these things, though, is that there's no guarantee of hitting that true maximum value. So other approaches that somewhat tries to address these sort of problems is this concept of simulated annealing. The basic idea here, it's almost like if you had a surface with a tabletop or something that had a topology to it. So there's up and down, and you got maybe a marble that you're rolling, and it rolls into, and you're trying to find the local minimum because gravity is a lot easier that way. Um, for the analogy, the problem is the same. It's just the matter of a sign, right? So you put your marble in, and it rolls to a location, and you may think it's the local, or you may think it's the minimum. You basically shake the table is how you can think of it. It lands someplace else, and it keeps going down potentially further. If it doesn't go down further, where you were before was better, so you keep track of where you've been, and you basically do that a certain number of times until you feel that you have. So it's almost like a random restart in that regard. Um, it, it's uh, it's an interesting guarantee. If T decreases slowly enough, will converge to optimal state. That basically means if you rattle it enough times, you'll get there. Is essentially it. Um, but again, these are variations of a theme of trying to uh, do it in a way that doesn't involve the exhaustive search, because this anytime you start looking at everything, you start entering this realm of big O notation, and it ends up being, long story short, it takes a long time, right? And it may not be feasible. So that's when we start doing other things, and we try to address that problem. And that's kind of the root problem of all of search is an exhaustive a complete search to find an optimal or a solution may not be feasible, right? So you do approximations that hopefully are good enough. Genetic algorithms have been around for some time, as I mentioned in the previous discussion. So um, it the idea here is to basically find the ones that are doing the best and uh, essentially keep trying with variations on them. And with that, we've finished our conversation around the search, local search and Optima stuff. Now we're looking at non-deterministic actions. So you've got this belief state that where you think the agent thinks how things are, and you have things that are supposed to cause side effects. So actions that do things that make changes either to maybe the agent itself or to the environment. Um, so the problem is that it's about somewhat around point of view and perspective and so on. Uh, so basically, the side effects don't always work out, is what it comes down to. So if you've got a robot vacuum, it may clean something other than what you think you're cleaning, and it may not clean the thing that it thinks it's cleaning as well as it does. Or maybe a self-driving car might not do quite as well on a wet or slick road or ice or something, right? So that's where it's kind of back to that whole closed loop sort of approach where you want to consider what the state is, especially whenever there's a chance that your action you took may not have actually taken. Another thing, I guess, to consider is that sometimes whenever you're dealing with actuators in a physical world, the the thing may not do exactly what you want it to do, either through mechanical failure, maybe something slips. So if you have a hand on a robot that's picking something up and moving it from one place to another, if it fell out of the hand partway through the process, if the robot wasn't smart enough to reevaluate the environment, it would assume it's one place and it's not going to be there. So it's not going to go terribly well. So there's always a chance of a certain amount of randomness and probability occurring in those sort of worlds. You've also got this concept of search inside of a partially observable environment. And this is typically where there's going to be either two kind of variations. There's no information at all. So there's a sensorless sort of world. Um, and you may need to solve the problem without sensing. Uh, can be challenging, but can be done. And then you may more commonly have information, partial information about the world. So you've got some information, but not totally all of the information, and it may or may not be totally accurate. So that's where you have this concept of a belief state. It's what you think the world looks like as you being the agent, and so you start with a prediction uh, based upon what you believe. You can compute the possible things that you may see, and you whenever you do the observation, and then based upon what you actually see, you update your belief state based upon what you saw. So it's a way of dealing with the reality of things where sometimes the world is not as simple as it seems, and certainly uh, we live in a random world. It's non-deterministic in nature. Things fall off of things, and sometimes operations don't succeed successfully. Another key sort of concept is online search versus offline search and unknown environments. Offline search, you compute the solution before any action is taken at all. So you figure out what you're going to do well before you do anything. Online search, you're doing it as you're doing the actions, you're reevaluating and recalculating and continuing. Obviously, that requires potentially greater computational resources, but it's very good for dynamic or semi-dynamic environments where things are changing. Um, and also in situations where time computing has a penalty, you may not want to sit and if you're playing a game of chess against a person, you may not want to calculate based on a given move and their move all possible moves that might could happen from that point in time. You may only want to go a certain number of levels deep because you may not have time to run those computations the whole way through. And you may end up with dead ends in online search that offline search might not be able to help you with because you may not know that you came or you're about at the edge of a pit in the metaphor of the Wumpus world. And with that, I'll conclude with questions. If for some reason any of this has sparked a desire to know more, do reach out to me, email, text, call, whatever is appropriate for you. That's what I'm here for. As always, stay safe, and I will talk with you next week.